This is a glass artist holding the start of their new sculpture. They begin heating the glass in a flame to form the sculpture, but the light quickly becomes so bright that they cannot see the details of what they're working on. If you were the glass artist, you might think to put on a pair of dark lenses, just like wearing sunglasses on a bright day to help you see outside. But now we have the opposite problem. Everything is too dark, and the artist again can't see their piece. In practice, glass artists use a pair of these special lenses. These lenses selectively block out the bright yellow flare while keeping everything else bright enough to see. In this video, we'll investigate the structure of glass to see why it gives off this bright yellow flare, and how we can then use the principles of glass science to give these lenses their unique property. Let's hand over to Ethan to learn more about the structure of glass and the origin of this yellow flare.
There are many different varieties of glass, but most are based on a silica network, consisting of bonded silicon and oxygen atoms. To meet the many different applications of glass, its properties must be tuned by modifying the structure of the silica network. For example, glass artists want a glass which can be melted controllably in the heat of a flame and can retain its clarity. To do this, glass artists use a form of glass containing sodium and calcium oxides. These modifiers break apart some of the bonds in the silica network, loosening the network and making the glass workable at a lower temperature. To understand what produces this yellow light upon heating, let's zoom into the sodium atoms. Each atom in the glass, including sodium, contains electrons, shown as circles, which occupy distinct energy levels. When the glass is put into the hot flame, thermal energy gets put into the silica network, and some of this energy goes to exciting the electrons of the sodium atom from their room temperature energy to a higher energy level. This higher energy state is unstable, and some of these excited sodium electrons may soon relax back into the ground state, releasing their energy as visible light. The color of light emitted depends on the energy difference between these two levels. Different materials have different electron energy levels, and so the differences between those levels changes from material to material. This means that each material gives off characteristic wavelengths of light, depending on its specific electron energy levels. In sodium, the difference between the energy levels corresponds to the energy of visible yellow light, which is why we observe a bright yellow emission. Glass artists know this characteristic emission as the sodium flare.
Returning to our original problem, we would like to have a lens material which absorbs the yellow light emitted by the sodium electrons while allowing all the other colors to go through. In 1875, British scientist William Crookes made the first glass-working lenses which performed this function. He did so by modifying the properties of the silica network using a newly discovered material called didymium. This material is still used today, and in fact, the lenses we showed you earlier also contain didymium. Didymium was first discovered by a Swedish scientist, Carl Mosander. At the time, he thought he discovered a brand new element. He decided to name his discovery after the Greek word for twin element, as its chemical properties were so similar to those of lanthanum and cerium, the two other known rare earth elements at the time. But if you look at the periodic table today, you won't find a box corresponding to didymium. It turned out that this twin element coincidentally ended up being a mix of two elements that were unknown to Mosander at the time, but you may have heard of now. So let's examine how the structure and properties of glass that we've learned can explain the behavior of these didymium lenses. Like the glasses we introduced earlier, these lenses are also made of silicon dioxide. Zooming into the electrons, we can see that adding didymium to the glass introduces new electron energy levels into the structure. This added energy level enables a new electron transition that just happens to correspond in energy to the light given off by a hot sodium atom. Consider what happens when the sodium flare reaches a didymium-containing lens. The energy of the yellow light matches the energy difference introduced by the didymium. This allows the electrons to absorb the yellow light by jumping up into the higher energy level. In contrast, other colors of light in the surroundings are not absorbed because the energy of those colors do not correspond to a higher level the electrons can occupy. As a result, the bright yellow sodium flare is filtered out while all other colors from the surroundings are let through. Let's head back to the lab to see this in action one more time.
In conclusion, let's evaluate how the structure and properties of our didymium lenses compares in performance to the dark welding shades. Recall that the welding shade made everything too dark as it was non-selective on which wavelengths it absorbs. In contrast, the didymium-containing lenses was engineered to selectively filter out the bright yellow light of the sodium flare while leaving other wavelengths untouched. This was done by making the connection that it is the same phenomenon of electron excitation which causes both the emission of light in the hot glass and the absorption of light in the glass's lenses. By changing the properties of the lenses to select a composition whose absorption energy is that of the sodium flare emission, the performance of the lens allows the artist to see the work of their formable sodium-containing glass and finish the work on their sculpture.